space, light is the fastest thing in the universe.
It could circle the Earth 7 times in 1 second.
As it reaches us across vast distances, it reveals the history of the cosmos.
We're able to look back in time.
Light travels at 186,000 miles per second. Its speed is an ultimate barrier. Nothing can go faster.
We have never, ever broken the speed limit.
But is the answer final? Will spaceships ever speed faster than light? Is it even worth trying?
To give up without trying is just giving up.
It can neither be touched nor felt. It is an abstract quantity of immense impact, the rate of motion at the very heart of all existence, the fundamental linchpin of the universe that we call light speed. Planet Earth, where speed is in demand, the fastest people, vehicles, and technologies seem to crawl in a cosmos where light speed is king. More than king, the speed of light is the cornerstone on which the universe is built.
There's a famous saying in physics, which is that the speed of light is not just a good idea, it's the law.
The speed of light is one of the most important speed limits in the entire universe.
The speed of light, 186,000 miles per second, is just incredible. I mean, if light traveled in a circle around the Earth, it could circle the Earth 7 times in 1 second. That's an incredible speed.
That incredible speed is the first thing we encounter when confronting the phenomenon of light. To say it is fast is a colossal understatement.
It's amazing to me that when I talk on my cell phone, I can talk to somebody clear across the country, and I'm not really aware of any time lag. And that signal is going from my phone to a tower, up to a satellite, back down, and it seems instantaneous. So we really take for granted the speed of light could practically be infinite to us.
Physics professor Clifford Johnson of USC is an avid bike rider. Circling a track, he considers trying to cover the same 186,000 miles that light does in 1 second. He'll find, however, that his work will be cut out for it.
To travel the distance that light moves in just 1 second, it would take me 22 months on a bike moving at 12 miles an hour, cycling 24 hours a day.
But the speed of light, in relation to the speed of life, makes our world work in just the way we've come to expect.
One of the beneficial effects for humanity of having the speed of light be as fast as it is that what you see is what you get.
Light speed makes everyday experience virtually instantaneous. When the light bulb goes on, you see it right away. Anything that happens around you registers immediately. And certain experiences make it crystal clear that light travels faster than anything else, including sound.
One interesting consequence of the great speed with which light travels is that you see a flash of lightning essentially instantaneously, but you hear the thunder only later on.
But light speed has its limits when stacked up to a place as large as the universe.
We think that the speed of light is unimaginably fast on a human scale. However, in astronomical terms, it's actually kind of hokey.
And so it's ironic that when the Apollo spacecraft blasted into space, traveling at what seemed an amazing 25,000 miles per hour, the speed of light proved frustratingly slow when it came time to talk to astronauts 236,000 miles away on the lunar surface.
So when the astronauts were on the moon and people asked Neil Armstrong, "Hey Neil, what's it like up there?" Several seconds went by between the question and Neil Armstrong's answer.
Neil, this is Houston, radio check, over. All right, Houston, lights clear. Roger, lights clear, Houston. Roger, bug.
And those several seconds were not because he was thinking about the answer, but rather because it took 1.3 seconds for the signal traveling at the speed of light to reach Neil from mission control, and another 1.3 seconds for his reply using radio waves to come back. And that's 2.6 seconds without even thinking.
Okay.
The 1.3 seconds it takes light to travel from the Earth to the Moon is pocket change compared to other celestial bodies. Light from the Sun, for instance, takes more than 8 minutes to get to the Earth.
If the sun were to disappear right now, if the sun were to suddenly vanish, it would take 8 minutes before we would even feel the shockwave and see the effects of a disappearing sun.
The limits of light speed also make communicating with Earth's far-flung spacecraft a special challenge. It takes up to 44 minutes for signals to travel back and forth to the probes exploring Mars, more than 3 hours to Cassini at Saturn, and over 29 hours to Voyager 1, the most distant of all, now heading out of the solar system. Still, these distances are trivial on a cosmic scale. We can almost understand the 10 billion miles separating Earth from Voyager. But what's next? The nearest star is a red dwarf named Proxima Centauri, nearly 25 trillion miles away. That's 25 followed by 12 zeros.
I am often asked a question, how can you as an astronomer really comprehend these vast distances, these huge numbers? And the answer is, I can't. The human brain really doesn't wrap itself around numbers that big. Occasionally, I actually write out how many zeros there are in kilometers from here to a galaxy, just to see how huge that number is. But in reality, of course, as astronomers, we would be spending all day writing zeros unless we came up with a better unit to use. And that's what a light year is. A light year is approximately 6 trillion miles. It's the distance that light travels in 1 year.
Using light years to describe distances opens up another dimension of light speed's character. Think of it. Sirius, the brightest star in the sky, is 8.6 light years away. That means we see it not as it is today, but as it was 8.6 years ago. We see the bright star Vega as it was 25 years ago, and the red supergiant Betelgeuse as it was 500 years ago.
It's a wonderful gift of nature that because it takes time to travel, we're able to look back in time. The further out we look in distance, the further back in time we look. We would have no idea what our cosmic history was if the speed of light traveled instantaneously.
Laura Danley is curator of the historic Griffith Observatory in Los Angeles. With light's ability to take us into the past, she's assembled a stack of photos that tell light speed's story of the universe in snapshots, looking back in time to its beginning, more than 13 billion years ago, to the present day.
I'm putting together a scrapbook of the history of our family of galaxies, and it shows all the galaxies that we can see with our telescopes as far back as we can see with our telescopes.
Each photo in this album, then, shows something in the universe with a look-back time equivalent to its distance in light years. The famous Crab Nebula, 6,500 years ago. The galactic core, center of the Milky Way, 26,000 years ago. And the Andromeda Galaxy, our next-door neighbor, 2.5 million years ago. But practically yesterday on a cosmic scale.
I love this cluster.
For almost 90% of the look-back time, the album is filled with common galaxies. Common, yes, but intriguingly diverse.
These two are colliding. You can see one going what appears to be right through the other. And there's a lot of drama in the way galaxies evolve and the way they interact with one another. So this one would be, it's only about 500 million light years away.
As Danley places each shot in the album, a bigger picture begins to emerge. Adult galaxies have been the main characters, evolving in all their variety for the past 12 billion years. But the cosmos also has its childhood photos, showing galaxies when the universe was a mere toddler.
These are actually very interesting galaxies at about 11 billion light years away. These compact galaxies are represent what might be a two or 2.5-year-old child, just really learning how to walk.
But even these galaxies have their younger brothers and sisters. This spectacular shot shows a gravity lens, a cluster of galaxies 2.2 billion light years away that bends light, allowing us to see much further in space and time. The lens reveals a tiny speck identified as one of the earliest galaxies we can see, as it was 13 billion light years ago, still an infant in the evolving universe.
Galaxies, when they were babies, really don't have a lot of distinguishable features. They're kind of blobs. They don't really have a lot of structure.
The universe as a whole was something of a blob at the beginning of its life, too. What we see of that time are the first light waves in history, reaching us only now, 13.7 billion years after they flashed into existence. We see them in the picture of an afterglow from the Big Bang. And they are known today as the cosmic microwave background radiation.
The cosmic microwave background radiation is the most distant thing we can see. It is, in a sense, the picture of the baby upon delivery.
NASA's all-sky picture reveals a glow that is uniform everywhere we can see. The universe as it was in a cosmic moment after its birth. But here, our view comes to a sudden halt. What we can see of the universe is limited, not by the size or power of our instruments, but by the barrier of light speed itself. How can the fastest thing in the universe make us blind to the infinity of space? Knowing that light speed is 6 trillion miles per year gives us the light year, a convenient shorthand for talking about the huge distances in the universe. But it's just as important to understand that light speed at 6 trillion miles per year is an ironclad constant.
The speed of light is so constant that the universe actually changes everything so that you never see it going any other speed. So the speed of light really is the measuring stick of the entire universe.
In fact, the constancy of light speed results in an amazing tool for measuring distance in the vastness of space. The tool is called redshift. It happens as light between galaxies travels at a fixed speed. When the space between the galaxies expands, the light racing between them gets stretched, turning red in color.
As light goes from one galaxy to another, from a distant galaxy to our own, for example, that light gets stretched along with the stretching of space. And that causes intrinsically short wavelength light, like blue light, to gradually become long wavelength or redder light. That fundamentally is the cause of the redshift that we see in the spectra of galaxies.
How does the redshift turn into a way to measure distance? It's all because of an astonishing discovery made in 1926 at the Mount Wilson Observatory outside Los Angeles.
Being up here at Mount Wilson is always a thrill for me because it was actually right here at this location that our view of the universe entirely changed. It was here that Edwin Hubble found out the universe is expanding. And that was an amazing thing. He wasn't expecting it. Nobody thought that was the case. And it changed everything.
Seeing red shifts everywhere, Hubble found that all of the universe's galaxies were moving away from each other, which we now know is caused by the expansion of space itself. As seen from the Earth, a galaxy doesn't look like it's moving away, but we know that it is because its light is redshifted. A galaxy moving away at low speed has a slight redshift. A galaxy moving faster has a larger redshift. But Hubble found that those faster-moving galaxies are also farther away. That meant the greater the redshift, the more distant the galaxy. By seeing how fast space is expanding and working the math backwards, cosmologists have been able to estimate the age of the universe. Combine that with light speed, and you have a major brain twister.
The universe is such a huge place that the light travel time really becomes important to us. We believe the universe began about 13.5 billion years ago. That means the farthest in any direction we can look is 13.5 billion light years. There hasn't been enough time for light to travel more than that.
It's called our light horizon, a sphere 13.5 billion light years in all directions, containing everything we can see. But that's where the brain twister comes in. Does space end there?
We have no reason to believe that the distance we can see is the entire size of the universe. In fact, it might be much bigger than that. It's just that with light travel time, that's all we can see. That's our horizon.
So consider this conundrum. Astronomers in a galaxy at one edge of our horizon can't possibly see any galaxies on the other edge of our horizon. But they can see galaxies 13.5 billion light years in the other direction. And so can astronomers at the edge of their horizon, and on, perhaps to infinity. As for astronomers on Earth, light speed has them trapped.
If we ask what is happening beyond our light horizon, we have to face the fact that the speed of light really is a barrier. We've never seen anything beyond our light horizon.
Can we take comfort in the fact that there is so much to see inside our horizon? This breathtaking shot is the Hubble Space Telescope's ultra-deep field. It's a massively detailed photo of an area of the sky 100 times smaller than the full moon, yet containing 10,000 galaxies, some whose light has been speeding toward us for 13 billion years. Beyond that is the cosmic background radiation from just 400,000 years after the Big Bang. In NASA's color-coded picture, the radiation's glow is pure green, representing a distribution of matter so uniform its temperature varies no more than 1/50,000th of a degree. Nothing in human experience is even close to this kind of uniformity. In fact, astronomers believe the universe should really be very different.
By rights, the universe should be lumpy. If you look in this direction and you look in that direction, you should see two entirely different concentrations of matter, different temperatures, but it's extremely uniform. Therefore, we have a puzzle.
The puzzle has its roots at the universe's birth in the Big Bang. If everything flew apart from the beginning, why shouldn't it be uniform?
No kind of explosion that we know about leads to that kind of uniformity. If you imagine an ordinary explosion, an atomic bomb, a piece of TNT, it's not really uniform at all. There's a piece of shrapnel going off there, a piece of paper going off there, an extra piece of iron going off there. It's really very non-uniform.
So scientists believe the cosmic background radiation just shouldn't be as smooth a green as it is. We can find out why in an ordinary paint store.
Let's consider a universe that consists of different color cans of paint. In our hypothetical paint universe, we have a can of yellow paint and a can of blue paint. And at the instant of the Big Bang in this universe, two cans of paint start expanding apart from each other. In our hypothetical paint universe, one side of it would look yellow, and the other side would look blue.
But as we've learned, the cosmos looks green, whether it's the paint universe or the real thing. The two colors of paint represent the different particles in the infant universe. To end up a uniform green, like the cosmic background radiation, they had to be touching. But when scientists first calculated the speed of the Big Bang, they concluded that it blew everything apart faster than the speed of light, meaning blue and yellow were too far apart, even at the instant of creation, for any mixing to take place. Through space, light is the fastest thing in the universe.
It could circle the Earth 7 times in 1 second.
As it reaches us across vast distances, it reveals the history of the cosmos.
We're able to look back in time.
Light travels at 186,000 miles per second. Its speed is an ultimate barrier. Nothing can go faster.
We have never, ever broken the speed limit.
But is the answer final? Will spaceships ever speed faster than light? Is it even worth trying?
To give up without trying is just giving up.
It can neither be touched nor felt. It is an abstract quantity of immense impact, the rate of motion at the very heart of all existence, the fundamental linchpin of the universe that we call light speed. Planet Earth, where speed is in demand, the fastest people, vehicles, and technologies seem to crawl in a cosmos where light speed is king. More than king, the speed of light is the cornerstone on which the universe is built.
There's a famous saying in physics, which is that the speed of light is not just a good idea, it's the law.
The speed of light is one of the most important speed limits in the entire universe.
The speed of light, 186,000 miles per second, is just incredible. I mean, if light traveled in a circle around the Earth, it could circle the Earth 7 times in 1 second. That's an incredible speed.
That incredible speed is the first thing we encounter when confronting the phenomenon of light. To say it is fast is a colossal understatement.
It's amazing to me that when I talk on my cell phone, I can talk to somebody clear across the country, and I'm not really